In this video, we'll be doing an overview of Lucas's proof on finding the Hamiltonian path on the flip graph. Recall that a flip graph is a type of graph where the vertices are the triangulations of any polygon. Two vertices of the flip graph are said to be neighbors if the triangulations differ by only one interior edge within a quadrilateral. This is known as an edge flip, as you're quite literally flipping an edge to get to another triangulation. For example here, all 5 triangulations of the pentagon are represented as nodes and are connected by flipping an interior edge. What makes these flip graphs special is that regardless of which n-gon we choose, we can always find a Hamiltonian path. That is, we can visit all the triangulations exactly once just through edge flips. Here, for example, is the flip graph of a hexagon. And as you can notice, the bigger the n-gon we choose, the more difficult it is to construct the flip graph and find a Hamiltonian path. However, it turns out Lucas's proof for this is actually quite concise and elegant, and so today we're going to show how she went about proving this. But first, we're going to have to introduce a definition from Lucas's paper, a way to identify each triangulation for an n-gon. This is what Lucas calls a code word, an n-2 tuple that uniquely corresponds to an n-gon triangulation. To get familiar with these code words, let's say we have this triangulation. How can we represent this triangulation as a code word? Well, the idea is that we want to count the number of interior edges coming out of each vertex. If we start at the top left vertex, we can see that there's 2 edges coming out. So the first value in the code word is a 2. Then we continue counterclockwise around the polygon until all spots in the code words are used up. So the next value is 0 since there's 0 edges coming out. Then for this vertex, we don't want to count any previously counted edges, so this value would actually be a 1 instead of a 2. And finally, there are 0 edges coming out of this vertex, so the final value would just be 0. So ultimately, the code word for this triangulation is just 2, 0, 1, 0. Now, let's go in the reverse direction. This time, we start with a code word and are trying to draw the triangulation. Suppose that we have the code word 1, 1, 0, 1. To construct the triangulation, the trick here is that we want to start at the end of the code word instead of the beginning. So, there's supposed to be one edge here, but to which vertex are we supposed to connect it to? Well, we want to start at the vertex we're currently at right now, and move counterclockwise until we're able to draw the interior edge that doesn't cause any crossings. After we draw the edge, we this time move clockwise around the polygon and continue to draw the interior edges based on the values in the code word. Now, for this vertex, notice that if we try to draw an edge here, we actually create a crossing. So, we want to move to the next vertex in counterclockwise order and make sure it's valid. In this case, we actually draw the edge here since it doesn't lead to any crossings. And so, this is the triangulation that corresponds to this code word. With our new code word definition, it would be a good idea to make use of it and check what happens to the code word if we do an edge flip. And so let's do that right now. There are 2 key insights we can get from looking at the neighboring code words. One of them is that for each neighboring code word, the sum of the values is always the same. This makes sense because the sum represents the total amount of interior edges for that triangulation. The other insight is when we do an edge flip, the code words always differ by plus or minus 1 at 2 different indexes, which is something that we taken advantage of in the proof. So now, with our background knowledge in code words, we can now move on to Lucas's proof.
Lucas uses something called stacks in her constructive proof of the Hamiltonian order. A stack of dimension d consists of the subset of all code words that share the same values in indices beyond d. So for example, this stack of dimension 2 has all the code words that share 0, 0 and indices 3 and 4. So we got index 0, 1, 2 here, index 3 and 4 are the same. So I look at all these code words, they all end in 0, 0. If I keep going, I'll eventually reach another stack of dimension 2 where the code words share 1, 0 at the indices beyond 2. The height h of the stack refers to the number of unique values that we can assign at index D. And so that's based on the fact that the entries have to sum to n minus 1 and whatever choices that we've made for the fixed indices. So here we can have a height of 4 because we can make the entry at index 2 0, 1, 2, or 3. And this next stack of dimension 2, we only have a height of 3 because we can make those values 0, 1, or 2. And so we're delineating all the stacks here with rectangles, and you see this nice recursive structure where once we fix a particular value, so let's say here we're at this 3-dimensional stack and we fixed this at 0, that gives rise to a substack, so where we fixed this at 0, of dimension 1 lower. And Lucas's key insight is if we arrange these stacks carefully, then we end up with, at the lowest level here, once all the choices have been made, we end up with the code words in Hamiltonian order. And the trick is that we want to arrange adjacent substacks in reverse order of each other as they go through their possible values. So here we see this substack at dimension 2 is going in ascending order of the possible values, and the very next substack goes in descending order of the possible values, and you continue to alternate that order. This makes sure that adjacent substacks line up where we're not changing by more than one value in the index, because you remember a valid edge flip, one of the necessary conditions is that 2 indices each change by exactly 1 from one triangulation to the next. So we have another tool that shows the Hamiltonian path by showing the triangulations and indicating the edge flips that happen one at a time as we go through that path. And then we're showing over here the substacks that we go through. So here we're going to switch from this one-dimensional substack, we're going to switch to a different one-dimensional substack that's adjacent to it. So we show all that stuff, and notice that exactly one edge flip is happening each time, and we'll eventually go through every single triangulation. But there's another thing that we get to show here for free, which is really cool. So it turns out, in addition to this correspondence between code words and triangulations, we also have a one-to-one correspondence between all possible binary trees on n with n internal nodes, where each internal node has exactly 2 children. We have a correspondence between those binary trees and the triangulations here. So let me jump up to and show you another example with n equals 5. So here we have a correspondence between triangulations of all these septagons here and binary trees with 5 internal nodes, including the root node, and also 6 leaf nodes in this example. So there's a one-to-one correspondence between the triangulations and those binary trees, and also an edge flip in a triangulation corresponds to a single tree rotation. So what we've gotten for free here is a construction of all possible binary trees, but traversed with exactly 1 tree rotation in between each one. And this is probably a structure and an operation that's much more familiar to most computer scientists who are trained in data structure. So this is also another way to explain what Lucas has accomplished here. So there have been some papers that have come out since Lucas's paper that have slightly conceptually simpler constructions of Hamiltonian paths and cycles. But as we show in our little write-up, Lucas's technique is amenable to a particularly simple implementation in Python, only 16 lines of code here, to construct the code words in Hamiltonian order. And once you got the code words, you have the triangulations of the binary trees. So thank you for your time. We hope this is illuminating, and thank you in particular to Joan Lucas for discovering this algorithm.